Today we will be looking at 3D Gaussian splatting for real-time radiance field rendering. It came out August the 8th. What is nice about this paper is that they use a new way to represent an object in 3D. Not only the object, but the scene. It could be a complicated scene. So in this case, what people used to do is they would have use this mesh here as you see here. They have a mesh, or they have voxels, or they have point clouds. These are explicit representations, and they're great for differential rendering. What's that? Is that when you render it, rendering means going from 3D to 2D, from a 3D shape to a 2D image. Differential rendering means you can back propagate through that. So you can go from the 2D back to the 3D. And they're great for that. However, when it comes to any topology change, like changing the angle at which you're viewing this 3D shape, it becomes extremely computationally expensive. So here instead of using a mesh or point cloud or voxel, they're using Gaussians. And what are Gaussians? They're something that looks like this. It's basically like a hill. Looks like a hill. It has a mu and it has a covariance. The covariance would decide how wide or narrow it is. Okay, sort of the shape of the Gaussian. So what is an example of an implicit representation? Well, it is like NeRF, which is neural radiance field. In NeRF, you don't store the points explicitly. The way you get the points is that you take for every you feed in specific coordinates into a neural network, and it would spit out the color and the density. The idea around NeRF is that you shoot a ray into the scene from a particular viewpoint through a medium. So that your 3D space is like a medium, which is differentiable. And then you see how that ray interacts with every particle within that ray. So for every, you shoot a ray right here, you sample some points. For every point, you feed it in the neural network, and then you would obtain a color and a density. And that's how you would sort of reconstruct it. After you would paint that, you would get all of those points, and then you would render them on a 2D scene. So as you can see, the information is implicitly represented. So what are the issues with the NeRF is that, which this paper aims to tackle, there has been some struggles in previous approaches like the NeRF. So this is really long to train. For every point, you need to evaluate it. You need to pass it through a neural network. It's very expensive computationally because of the for every point in a ray, you need to sample that. You need to take a sample and you pass it to the neural network. Another disadvantage of NeRF is that, as you can see here, the cameras are taken within a distance from the object. So this is like a bounded scene. It's not it focuses on the object, and the distance between those views and the object are relatively the same. That's why it's creating like a sphere here. So it struggles when you zoom into the object or you zoom out really far. It actually struggles because it's trained on views from a similar range to the object. And lastly, the issue with this NeRF is that it's really about objects, which is fine, but the paper here is going to also focus on complicated scenes. As well, here there's an object, but all of the stuff around that object, you can do any scene with that. Okay, so what makes this paper stand out? It's not that it has a differential renderer, which means when rendering means you're going from 3D to 2D. Differential rendering means you're able to go from 2D back to the 3D and adjust the parameters. What makes this special is that by using 3D Gaussian, another prior, they're able to make this fast, so the training time is low. You're rendering in a fast way. You're rendering high quality, so it's really high quality, and it's not object centric, so you're not just focusing on an object like here. It could be a scene, and so why, like, one of the ways they do this is it's that with the Gaussians, the Gaussians are like an army where you send the soldiers to where the part of the scene that needs a lot of work, that has a lot of details. You can send a bunch of them there to represent the intricate detail of that scene, and the areas where there's less details, you don't need to send as many soldiers, if that makes sense. There will be less Gaussians. So that's a part of the training that we're going to cover a bit soon. Another thing about the Gaussian is that they're able to actually change shapes and positions. Okay, so I'm going to move a bit forward here. Like, what are the parameters of the Gaussian? It's the position. Okay, so that's this one here. There's the opacity, which is the see-through. There's the anisotropic covariance, which is isotropic covariance is when the Gaussian, which looks like this, right? These are isotropic. So if you can see here 0.6, 0.6, the diagonal is the same. So everything is symmetric. But if you look from the top, it's like this. But an anisotropic Gaussian is when you can play around with the shape. So it can be, instead of it being like this, like everything is symmetric, it could be more like this, right? Where here it's more dense than further parts, and so that's really important because this allows you to actually align. Let's say you're trying to model the shape of the wheel here. Well, like here, for example, the Gaussians would have to actually move around and align and rotate and shear and all of this stuff so that it actually matches the ground truth image. So the anisotropic property is super important, and so they're able to use that. We're going to see later that it's actually not exactly a Gaussian 100%, but if you actually look from the top, it's more of an ellipsoid. So technically speaking, they would be using an ellipsoid, which is the scale, how far it stretches this way, how far it stretches this way, and how far it rotates, and we're going to talk about that. So just to recap, the shape depends on the data variance, and that's important because as you change the angle of where you're viewing the object from, the whole scene is going to change. So you need those Gaussians to shear and rotate accordingly. The next thing would be spherical harmonics. What are spherical harmonics? These are, I have a picture here. Basically, what they do is that they encode how the light and the shadow behave on a curved surface based on the viewing angle. So as you move, as you're moving around, you're changing the view of it. From a different angle, the lighting is gonna change, gonna reflect, and so instead of computing the light interaction at every pixel, you actually have functions that approximate it. They estimate it for you. They will give you the brightness and all of that stuff. So instead of storing the actual RGB values to represent the image, you'll have equations. And those equations are the spherical harmonics. So all of these parameters, so the position, the see-throughness, the shape of the Gaussian, and how the light and the shadow is going to behave on the surface based on the angle that you're seeing. These are the parameters that we're going to need to tune to model the 3D shape. An extra note here's interleaved with adaptive density control. It's basically when I talked about the army that is sent to the detailed scene so that they can work on those specific details. These first few parameters, what's in yellow here, is updated at every iteration, and every 100 iteration or so, they sort of take a look. They take a view from far, and they say, okay, do we need more Gaussians here, or do we need to delete some Gaussians over there? Okay, I just want to see if I missed something here. Okay, here I just put an image of if you have multiple Gaussians, let's say you have 3 Gaussians here, you can combine the Gaussians together to actually make up what you see here. Okay, so there's about millions and millions of Gaussians here, and they all interact with each other in a way that I'm going to explain, that will give you this final image. So what does the algorithm look like? The algorithm is down. Okay, let me actually just read this. Our goal is to optimize. So what is their goal? Their goal is to optimize a scene representation that allows high quality novel view synthesis. So this means a new view that we've never seen before of that object, starting from a sparse set of SFM. SFM stands for structure of motion. SFM points without normal. So what's SFM? You take SFM would be these points here, like this is 1, 2, 3, these are the points. Basically, you would take a shot, a picture, like many pictures from different angles of the object, and you would use a tool like Colmap, for example, to actually triangulate, find the correspondences, find similar features of this object from different point of view, and then trying with the camera settings and triangulation, it will basically find very sparse points of this object in 3D. So this is what they start with. They start an initial guess. This is a guess of what the object or the scene look like in 3D. Okay. To do this, we need a primitive that inherits the properties of differential volumetric representation. That's your Gaussian, while at the same time being unstructured. Okay, so and explicit to allow very fast rendering. So we spoke about how Gaussians, they're explicit. You can see the shape is already there, and it's unstructured. They can move around, they can change a topology, they're not fixed, right? Like the nerf here. This is not, they're not fit, it's not a grid, like a 3D grid or something like that. These things, they move around. Okay, so we chose 3D Gaussians, which are differentiable. That means you can go from 3D to 2D and from 2D back to 3D, and can be easily projected to 2D splats, allowing fast alpha blending for rendering. Alpha blending means let's say you have many Gaussians, and each one has its own opacity. You're actually going to take a bunch of them into consideration. You're going to blend their opacities together to get the final color from that particular viewpoint. Okay, so this is what they do. So what does the pipeline look like? So we start from structure from motion points. This is the guess that we get from a tool like Colmap. Okay, for every point, okay, we're going to convert a point into a Gaussian. Okay, right, so we have the algorithm here. Okay, here what do we have? So we're going to take your SFM points. You're going to get your Gaussians. Okay, these are the position. The M stands for mean. You're going to get the positions of the Gaussians. You're going to initialize your covariance, the colors, and the opacity. Right, the covariances, the colors, and the opacity. A is for opacity. And then you're going to go through the loop. Okay, the first thing you do is that you're going to get your image, and you're going to get the view of the camera. Right, this is like sort of, yeah, sorry. That's the view of the camera. That's your V, and you get the image. Okay, so what do we do next? You're going to get the positions of the Gaussians. Okay, you're going to get your millions of Gaussians and the initial value of the covariance. What's the covariance? It's the shape of the Gaussian. You're going to get the colors of the Gaussian, which at this point they're random, and the see-throughness and the view, and then we're going to rasterize. What does rasterize mean? Rasterize means you're converting from, you're taking a 3D shape and you're displaying it in a 2D view, specifically with the pixels. You want to know every pixel, what's the color of it, and then you're going to get the image. So let's zoom into this function here, rasterize. Okay, what does rasterize do? Okay, so rasterize, the first thing we do is that what's this P here? Okay, they don't, yeah. So the first thing you're gonna do is that from a particular viewpoint, okay, you're gonna only keep the Gaussians observed from this viewpoint here. Not all Gaussians are going to be seen. Like, for example, let's say the back of the, let's go back here, right? You have the back of the bike. You cannot see the back of the bike, or you cannot see what's outside outside the what's next to the bench, what's like 2-3 meters away from the bench. You don't see that, so you don't care what's there, so you filter those out, right? Next step would be screen space Gaussians. Basically this is where you would project the Gaussians to image coordinates. Okay, so you're gonna go from your 3D, you're gonna go from your 3D worldview to 2D. Okay, how do you do that? There's a function here, which it's J times W. Okay, what is J? J is a matrix. Okay, it's a Jacobian matrix. It has the derivatives to project the image from the camera coordinates to the image coordinates. Okay, the W is a viewing transformation matrix. It transforms your world coordinates to camera coordinates. Okay, and then the sigma here is your Gaussian covariance matrix. So this is what holds all of your the means and the scale and the rotation of those Gaussians. So basically what goes on is that we take those 3D, that's 3D, okay, we multiply it by two matrices. Okay, both of them are going to act as your extrinsic. Okay, by multiplying W with sigma and with W transpose, you're actually, it's like you're taking your 3D shape and you are transforming the 3D shape to camera coordinates. This is in world coordinates. Okay, so this is in world coordinates, and then after we multiply this, we get camera coordinates because these are the extrinsics, and then we multiply by the Jacobian J times all of this, okay, times J transpose. These are going to act as your intrinsics. And intrinsics, they map from the camera coordinates to the actual 2D pixel coordinates or your image coordinates. And you're finally going to get how these are going to look like in on a 2D plane. So that's the point of the screen space Gaussians. Okay, so just wanted to mention about your this covariance matrix. What it really is that you couldn't really actually work directly with the Gaussian because the Gaussians they're represented by covariance matrix which have a property which is very difficult to use in a neural network. This requirement is that the matrix, so when you have a Gaussian like that, you have a covariance matrix like 0.6, 0, 0, 0.6. There's a property that says this needs to be positive semi-definite, which it seems that it's very difficult when you're training, and so they actually, if you look from the top, it just looks like an ellipsoid, and so you can have like it's basically dense here and then it's less dense, right? And so the scale in the x, y, and z coordinates, that's stored in a matrix called S, and your rotation is called in a matrix called R. So what you're actually trying to tune is actually the ellipsoid right here. So what's actually in that sigma here, the information of all of the Gaussians and their scale and rotation, it's actually you take R times S times ST RT. There's some symmetry here, hence to satisfy the symmetric characteristic. So that's part of the that's what is used. You multiply by W and WT to move from the world coordinates to the camera coordinates, and from use the Jacobian to move from the camera coordinates to the image coordinates, to finally get a 2D image. Next, you go to create tiles. So the image, let's say your bicycle is like this, okay, and then there's like there was the bench somewhere here. Sorry, this is not very aesthetic, but what happens is that actually you would compose this, you would put this in a grid, in sort of a 16 by 16 grid, and each one of those squares are tiles, so it's a tile-based rasterizer, as it's mentioned here, somewhere on the top. So we introduce a new approach that combines the best of both worlds. Our 3D Gaussian representation allows optimization with SOTA, visual quality, and competitive training, while our tile-based splatting solution, and so in the past it was pixel, this was a per pixel based splatting, now it's a tile based, which makes things faster. And so they create tiles. They take the height and the W and the width, and they get the tiles from that. And then here you're going to duplicate with keys. What exactly are you duplicating? When you create the tiles, there's going to be many Gaussians that sort of intersect, right? Some of the Gaussians are inside, some of the Gaussians are outside. Some of them, so there's going to be many that are going to intersect across the tile. So we want to duplicate that and have separate keys for that. And why do you want to do that? Because within each of the tile, we're going to sort. What exactly are we going to sort? Because this is a 3D, so you're in a 3D shape, you have some Gaussians that are in front of other Gaussians, depending on where you're looking from. And these might be in a particular tile. So each of the Gaussians is composed of a key, which is composed of two parts, the tile ID and the depth. Okay. And so that's where your sort by key is. So you're going to sort by the tile ID. So within a tile, you're going to sort by depth, and they talk about a radix sort. That is done on the GPU. It's just a very fast way on the GPU to actually sort all of that. Right, so the identified tile ranges basically just going to return a list of those Gaussians, and then for all the tiles and all of the pixels, we're going to loop through all of the tiles. We're going to loop through all of the pixels. We're going to get the list of the Gaussians at that tile, and then we're going to blend all of the pixels. We're going to accumulate the color and the see-through values by traversing the list of the Gaussians from front to back. So all of these are going to be blended together to finally get your rasterized 2D image right here. So that's a 2D. Okay. And so that's a one pass through your rasterize function. So this is called, back to the main algorithm. Once you have your rasterized image, you're going to compare your ground truth with the image you've rasterized, and you feed that into your loss function, which is what? The loss function is somewhere it is, find it, it's here. I think lambda here is 0.2, but you're trading off between a L1 loss, so you're matching every pixel with each other so that the image is identical with each other, but you're also comparing your DSSIM, which this focuses on a few things. It focuses on the structure, which is very important, just like how structurally similar. If you just focus on the L1, you're not going to get great results. And of course, if you just focus on the DSSIM, it's not going to be good. You could have a high score in the DSSIM, but it could be blurry. And here it could be a high score, but it could find another way to make the pixel values the same, but structurally it's not the same. So having a trade-off here will make sure that the pixel values are really close to each other and the structure is the same. You also have the luminous, the luminosity of the images and the contrast of the images. So that's your loss. And you're going to optimize with the atom, right? You're going to get new value. You're going to get the gradients for your mean, your covariance, the colors, and the opacity. Okay, and then you're going to loop through that. Every now and then, okay, so is refinement iteration. Every now and then, I think it's 100 iterations or so, you're going to look at all of your Gaussians. And if a Gaussian is If it's very see-through, then there's no point in having the Gaussian. You remove it. Besides that, the next thing is when I spoke about the analogy of the army, where you send the army to the parts of the image that have a lot of details. And they talk about it here. So let's say that's an area where it's under reconstructed, so it's missing geometric features. So you want to send more of the army there. So basically what they do is that they clone. They clone and then they stretch it out and they rotate it and move it around so that it covers the area, right? The other situation is where actually the area that one Gaussian covers, it's a very large one. The area is too detailed for one Gaussian to work on. So we need to split the Gaussian and continue the optimization. So this is what they do here. And like I mentioned here, it's crucial for good background reconstruction. This is one of the ways actually how it outperforms other methods. You're able to send more parameters to the area of the image that needs more construction, unlike other methods. So just to summarize here, you start with your structure for motion point. Every structure for motion point is converted to a Gaussian, project that to 2D. You rasterize it. We spoke about this method right here, and you get the image, right? And then you would compare it to your loss function right here, and then you would get your loss, get the gradients, okay, the new updated values of your parameters of the Gaussians, and then you would do your every now and then. So the differentiable is you go from this back to 3D. You would run through your adaptive density control, which is it's where you send more Gaussians to the part that needs more, or you would remove the Gaussians where it's not needed, and you would loop. That would be your training. This is the first paper I review. Thanks for listening, and I hope this helped you understand the paper more. Thanks.